This is Dr. Mohanlakshmi, Professor and Head, Department of Electronics and Communication Engineering from Rohini College of Engineering Technology, Kanyakumari district. So, in this video lecture, this is the fifth unit, which is multistage amplifiers. So, we'll see what is multistage amplifiers, and of course, we'll see very briefly about the cascode amplifier. So, multistage amplifier, we have various characteristics. Say input impedance, output impedance, phase angle, voltage angle, current gain, power gain, right. So when I'm going to use common base, common emitter or common collector configuration, of course as it is tabulated, the various characteristics varies. So common amplifier is most popular BJT amplifier due to the high power gain. So the power gain will be very high. That's the reason we use always a common emitter amplifier. So ideal amplifier should have high input impedance, low output impedance, high voltage and current gain. Single stage amplifier is not able to provide enough gain, power and fulfill all the requirement of an ideal amplifier. So that's the reason we go for a multi-stage amplifier. So multi-stage amplifier, we have various stages. You can go up to 4 stages. So it could take different combinations. Say for example, I may have both common emitter, one common collector, or I may have with the common collector, common emitter, common collector. So whatever be the thing. So you have this has been described with various characteristics. Resistance input resistance, output resistance and the voltage gain. Okay, so the downwards it is given what would be the real description of these values. So what is low, what is medium, what is high, what is very high, what is extremely high. Okay, so in one particular combinations where you have all the stages to be common emitter, you can see voltage gain is very high. So multi-stage amplifiers, it consists of number of stages connected in cascade. So this will be usually required to provide high input resistance, high common mode rejection for a differential amplifier. So normally that will be provided by the first input stage, whereas the middle stages will provide you majority of the voltage gain, conversion of the signal from differential mode to the single head mode, shifting of the DC level of the signal. The last output stage is to provide a low output resistance in order to avoid loss of gain and provide the current required by the load. That is normally used for the power amplifiers. So we have the frequency response for the multi-stage amplifiers. So you can see here the voltage gain, it is represented here as 1 by root of 1 plus f1 by f the whole square. Similarly, the low cutoff frequency, if I have identical stages, then the overall voltage gain at the lower frequency can be given by the multiplication of the n number of stages. So the n represents your number of cascaded stages. For lower cutoff frequency, you can see what will be the frequency output, which is given in the shaded thing. And similarly, multi-stage amplifiers, we can obviously use it for high cutoff frequency, and you could see the various expressions associated for the high cutoff frequency. So normally the cutoff frequencies for cascaded amplifiers, this will be identical values. This has an identical value of FC1 and FC2, which are found using the lower frequency cutoff, higher frequency cutoff, and what would be the bandwidth. So the n represents as usual as a number of cascaded stages, when each stage has a different lower and upper critical frequency. Okay, so here lower critical frequency is given by FCL. So this is for each amplifier stage, this will be different. Okay, so here similarly the upper critical frequency, here also for every stage it will be different. Okay, So that's what it is given over here. And coming to the one type, so there you have a cascade type, you have a cascode type. So cascode is the amplifier we are going to see now. It is a combination of common emitter and common base amplifier. So while the CB amplifier is known for the wider bandwidth than the common emitter configuration, the low input impedance of common base is a limitation for many applications. That's one reason we normally don't prefer a common base. The solution is to precede the CB stage, that is the common base stage, by a low gain common emitter stage, which has moderately high input impedance. So can you see, like the common emitter will have a high input impedance, and whereas the common base will have a low input impedance. So in order to compensate this, we put a common emitter in front of a common base. So the key to understanding the wide bandwidth of the cascode configuration is the Miller effect. So this common base configuration is not subject to the Miller effect because the grounded base shields the collector signal from being fed back to the emitter input. Thus, a common base amplifier has better high frequency response. So the way to reduce the common emitter gain is to reduce the load resistance. Say it is approximately RC by RE. So the collector load resistance is the resistance of the emitter of the CB stage loading the CE stage. So C gain amplifier is approximately, it is given to be RC by RE, which will be equal to 1. So the Miller capacitance is given by the expression which is shown in the slide. We now have a moderately high input impedance at the C stage without suffering the Miller effect, but we have C stage voltage gain is less or nil. The CB stage provides a high voltage gain, so we get a high input impedance as well as a high voltage gain. So the total current gain of the cascode amplifier is beta, as the current gain of C stage is 1 for the CB collector base junction is beta. So the cascode amplifier has a high gain, moderately high input impedance, high output impedance and high bandwidth. Thank you.